once we're through that, we can set a new milestone, and that is writing our own specification for a new power supply, for something that replaces the original Amiga power supplies. And solving this will be possible with a DC-DC converter. We're going to look into the basics of how this is working, and how we need to modify this with a compensation circuit. So let's jump right into it. The existing solutions are, of course, the original Commodore PSUs. There is the heavy type, the transformer-based power supplies, and the later models are lighter and more powerful. Those are switch mode power supplies. The second source solutions are basically mean well based. These chassis are high quality and easy to use. Several vendors are using these to make Amiga replacement power supplies. Then there is a second source that uses a Cisco power supply, one that has specifications very similar to the original Amiga power supplies. And this slide still shows that we're going to look at ATX power supplies, or modified ATX power supplies, which is basically a very bad idea. But I don't have any slides about that. If we got time left at the end, I will attempt to say a few words about that. So let's jump into it. The original Commodore specification. Lucky find, as I said earlier. I gave you the URL where you can read the whole specification here. And by the way, I will make the slides here. I will make them public, and therefore you will also have this link. So if you read that specification, those are very strict specifications. They are, here is the load regulation that requires the 5-volt rail to be accurate to plus minus 5%. The 12-volt rail is required to be plus minus 10%, and the minus 12-volt is also required to be plus minus 10%. Now, this is rather easy to achieve, though not the way that Commodore requires measurements. Ripple and noise, here's another hard one, 50 millivolts on 5-volt DC. That's also quite hard. I need to tell you what ripple actually is. Ripple is an AC part that is on the DC voltage. If you measure the DC voltage with an oscilloscope, you see basically you see the voltage jumping between values, and this needs to be, well, lower is better, because if this is high, then a high amount of current is flowing in capacitors, for example. This causes the capacitors to heat up, and heating up means a shorter lifespan and reduced capacity, higher internal resistance, and in essence, when these capacitors age, they don't have the original effect anymore. Practically no effect after the 20, 30 plus years that these power supplies have been working. Now, here's another one. The initial setting must be within 50 millivolts range. That is 1% precision. Luckily, 12 volt and minus 12 is not required to be set at anything. And there is overcurrent protection. Although those power supplies, this one here is rated 3 amps only, but the power supply must be able to supply 8 amps, at least for a brief period. This is kind of hard to achieve. So let's, first of all, let's see how we measure this, because putting load on a power supply is kind of hard. You can use electronic loads, but those are problematic. problematic because they are electronically controlled. They don't they have a little microcontroller, and if you say I want to draw like 5 or 10 watts, then the whole setup might start oscillating, and then you are basically measuring the oscillation circuit that you've built between your power supply and the load, but you're not measuring the power supply. So the easiest thing is, of course, to hook up resistors and have them convert all the power into heat. And that's what I've done here. I have built a little setup with lots of load resistors. Here is a small load resistor that actually also has a smaller value, 2.7 ohms. The other resistors are 10 ohms. So if you feed in 5 volts, you should be, you are seeing 500 milliamps of load. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9 times 500 milliamps. So added on those about 1.9 amps, I can add another 4.5 amps on the 5 volt rail. And this part below here, I have used more load resistors to load the 12 volt rail. This one here, this wire, by the way, all these wires are really thick. They are the thickest copper I could find in my lab. So these are actually speaker cables. I think they are 4 millimeters square. So the voltage drop on these is really low. What I've done here is I've taken one of those 5-pin square DIN connectors that the Amiga 500, 600 and 1200 is using. And I have soldered this to the input filter, the line filter that these 3 Amiga models are using. And this is to get an accurate reading of what kind of voltage would arrive on the main board. So I call it the usable voltage by the Amiga. So yeah, this 12 volt part here is also switchable. There are 2 resistors, 120 ohms each, and they represent a load of about 200 milliamps on the 12 volt rail. Next slide. The measurement setup. What you see here is how I've set this up. This is an oscilloscope, actually mixed signal scope, but I'm not using the digital part here. Up here, that's a power analyzer. Really nice gear, Rode und Schwarz. And here's a voltmeter, Uni T, that's 6000 count precision. Here's a clamp amp meter, also a Uni T, 6000 count precision. And here's a voltmeter, that's just a 2000 count for displaying the 12 volt rail. This is the device under test, and these power supplies there, they are not used. Those are lab power supplies. Just ignore those. So one little detail about measuring ripple is in the original specification that I have extracted here. Ripple and noise shall be measured with an additional capacitor or 2 capacitors connected. That's a 10 mic for electrolytic, and a 10 nanofarad or 0.01 microfarad capacitor. Those are typically ceramics, and that's what I've soldered on here. Hope you can see this. And yeah, taking you through all the measurements would take way too long, so I have taken that time prior to this and came up with this diagram. The diagram is generated with LibreOffice. I will publish or make it available. Not sure where. I'm not sure whether the revision guys or I will provide the web space for that. Maybe just on our support forum. So what you see here is a diagram of the 5 volt rail versus, here's the voltage on the y-axis, and on the x-axis is the load in amps. First of all, this is the blue one is the Amiga 600 3 amp rated power supply. And this is starting off just under 5 volts at 1.8 amp load, and it's dropping rather severely. But as you can see, I can it is still holding up at over 5 amps of load. And then all the other ones, here's an Amiga 500 power supply, the heavy type, the 2.5 amp. The yellow one is the 1200 Amiga power supply. That's the longish one, 3 amp type. And the green line here, that's the 4.3 amp Amiga 500 power supply. That's something that's being celebrated in the forums as being the best you can get. But what you can see here is that, well, of course, there are also the Meanwell-based second source and the Cisco ones. The Cisco kind of points out here because the falling curve here is not as steep as with the other ones. But altogether, all these power supplies tend to drop the voltage fairly low under load. And that's generally a bad thing because under a certain voltage, new hardware that uses modern 3.3 volt components has problems to maintain that 3.3 volts. That's basically because the regulators used are low drop linear regulators, and if they don't have enough regulation overhead, they tend to oscillate. So if the voltage drops below 4.8 volts, then the regulation, the overhead, the dropout voltage in those regulators gets too high. They start to oscillate, and as a result, the 3.3 volt components might get a latch up. So those are then damaged beyond repair and need exchange. In essence, they need service. And that's what we observed here. Now, next measurement is ripple. And you can see here that the existing ones all have fairly high ripple. The mean well is particularly bad. I've been saying on forums over and over again that using a mean well power supply is a good idea for many applications, but not for the Amiga. And this is a clear answer here. It just violates the specification from Commodore by a factor of 2. But then, of course, if you look at the other power supplies, they also have rather high ripple values. It's just that Amiga 600 one that stays below 50 millivolt ripple. Sorry. And just by coincidence, that's the power supply I've been using to develop most of my accelerators. So let's sum up the observations here. We've seen that the voltage drops linear with the current. That voltage graph you've seen before, all those curves, they are linear. The voltage, you can almost put a ruler on there. Ripple is out of spec. Then the overload behavior of the Cisco PSU, that is something I did not show, but I did observe, and you will see if you review the table with the original measurement data. As I said, I will publish all the original measurement data, the open document ODS calc, the calc file, and that Cisco PSU just switches off when 30 watts load are exceeded. So that overcurrent behavior that is specified in the original Commodore specification is violated by the Cisco PSU, and it is violated in a bad way. It's going to hiccup mode. That means it's switching the 5 volt rail off and on until that overload is gone. And another observation, which you will see if you review the data is that the 5-volt rail changes with load on the 12-volt rail. Now, each of these observations, of course, have reasons. The voltage drop is caused by Ohm's law. All of these power supplies are regulated, have a regulation loop that is within their own box. This regulation loop looks at the local voltage, at the voltage that is being sent from the CPU. Not the CPU, I'm sorry, from the power supply, from the PSU. And then the voltage needs to go through the cable, through the connector, which has a resistance, then through the line filter, which also has a resistance, and only then it can be used inside of the computer. So all those little resistances, as small as they are, they exist. There is no such thing as lossless transfer of energy, and the loss is described by Ohm's law. And here's where equations would have come in, but they aren't. But there's just a linear equation. Just remember linear equation. Second, the ripple. Of course, these are all PSUs. The power supplies have not been serviced. They are in their original state, and therefore the output capacitors are 30 plus years old. So I wouldn't have expected them to comply with the original Commodore spec. But as you've seen, they hold up quite nicely. So continuing to use the original power supplies might not be that much of a bad idea. Then the Cisco PSU, well, it's just built like that. The hiccup mode is a common and widely used mode to deal with overcurrent or short circuit situations. And I would just recommend not to use such a power supply. If you do not have an expanded Amiga, then it might be okay. But as soon as you have something new in that Amiga, something that uses 3.3 volt logic, then you should put that Cisco power supply to rest. Now, that fourth observation, the 5-volt line or the 5-volt voltage dropping when the load on 12-volt changes, that is a little harder to explain. I have I'm trying to prepare something here. Just a second. Here is the culprit. Let me show you. Maybe we need a little more light, if that works. Here is the input filter as used on the Amiga 500, Amiga 600, and Amiga 1200. You see a total of 8 terminals, 4 inputs and 4 outputs. And they are used for, of course, for 5 volts, for 12 volts, for ground, and for the minus 12 volt rail. That means we have a common ground. And this means the return current of the 12 volt rail goes through the same wire as the return current of the 5 volt rail. So that is the main reason why the 5 volt rail drops with changes in the 12 volt load. Now, how can we, is this really the right slide? Okay, I'm sorry, got distracted. Now, there are a few possibilities to work against voltage drop. Of course, you can always use thicker wires, you can shorten the cables, but that will never get you off that linear behavior, and you never know what kind of load people are putting on those power supplies. You don't know in advance what kind of system the user will have. So if you are offering a power supply then just using thicker wires and shorter cables might not be the best idea. Another idea that people might have, and to be honest, I had it too, that was using the shield line as an additional ground line, and that would reduce the cross-regulation problems between 5 volts and 12 volts. But then, of course, the filtering property of that input filter, of that line filter that I just showed you, would not it would be totally jeopardized. That input filter works in current compensation mode. So whatever flows in one direction causes a magnetic field in that in that ferrite that the windings are on, and the that same current that flows back causes the same magnetic field, but with a different sign. So in essence, the magnetic field is always near zero, or that ferrite material can never go into saturation, and that's exactly what you want if you want a filter. So using the shield would mean, as a ground, would mean that part of the current would bypass the filter. And that is a free way for EMI, for electromagnetic interference, to enter the whole world, and that would immediately cause radio interference if such a power supply would be operated. So using the shield line as an additional ground is a bad idea. Now, some more sophisticated ways would be using a sense wire. And that is to widen the regulation loop. So you don't regulate within your power supply, within your box, but you are sending the voltage to the connector of the Amiga, and then have another wire that goes back into the power supply. So the power supply knows about the voltage drop on the cable. But of course, you can only measure up to the point where the voltage enters the connector. But there is another voltage drop, and that is in the line filter. So the sense wire is only the second best solution, and therefore the current dependent voltage adaptation is the method of choice here. So in essence, you need to measure the current that is coming out of the power supply, and depending on that current, adjust the voltage at the source, so it'll be constant at the point where you desire it to be constant. And since the resistance of the cable, the resistance in the connector, and the resistance of the line filter is known, this can really be compensated within the power supply. Now, we're at a point where we can really get to specifications, and of course that is clear. The Amiga 500, 600 and 1200 models shall be addressed, because those are the ones with external power supplies. Luckily, they all use the same. The power supply should handle lots of expansions, and this includes not just an accelerator, a flicker fixer, but also the old type of expansions that people had, and that's a stack of external drives and maybe a CD drive that leaches a lot of current on the 12-volt rail, especially when they spin up. And I've seen lots of modded Amigas, and I would have really looked forward to seeing all those modded Amigas at revision. Unfortunately, we're all at home, and all those Amigas didn't travel to a single place, so I can't see them. But yeah, those modded Amigas, they have lights in them. Those are probably connected to the 12-volt rail. But yeah, another thing is we never want to drop below 5 volt, because yeah, I know you Amiga guys, you always want the best power, And the best power means you want to overclock your accelerators. And Motorola CPUs are overclocking capable, but the higher you go, the more precise the voltage regulation needs to be. And my personal observation during development of the accelerators, especially the 1221 LC, has been that it works nicely at 40 megahertz with a good power supply. And as soon as the voltage drops below 4.9 volts, then 40 megahertz operation becomes unstable. But then, of course, the 1233 55 megahertz version, which has just been out for almost a year now, that is overclocked from the factory, and this of course also gets unstable when it gets insufficient voltage. So we do not want the 5-volt rail to ever drop below 5 volts. We want the thing fanless. We don't want it to be as noisy as the Amiga 2000 or even worse things. And then of course, if a floppy drive starts spinning, it draws additional power on the 12-volt rail. If a CD drive starts spinning, it draws lots of power, especially those 40, 50x drives. And varying load on the 12-volt rail shall not impact the 5-volt stability, because if you run an overclocked Amiga and you insert a CD, and upon spin up of the CD, your Amiga crashes, not a nice thing. Then one thing that I really didn't like about the Commodore power supplies was that the switch is at the power supply, but in my setups I've always had this, the power supply somewhere in a hidden place under the table or so, where it's not really easily accessible. So I personally would like to have the switch near the Amiga where I can switch it on and off. But that might be just me. But yeah, well, I primarily built the stuff for me. And well, then hopefully the community likes it. But then, of course, there are legal constraints. And those legal constraints need to be handled by a tiny company like Individual Computers. Like I said earlier, it's just 9 employees, including me. And this size of company, we just cannot handle really huge legal things. So how do we get around the legal constraints? First of all, a power supply is mains connected. 240 volts maximum in Europe. That is dangerous to your life. So there are laws about safety. There are safety rules to comply with. Those tests must be taken in or by official labs. And the cost of running through all those tests to get global compliance are around 40,000 euro, and that is just way out of the budget of Individual Computers. So as a result, it would either be now do a little calculation. Let's say such a power supply would sell 1,000 units. 1,000 is a huge number for the Amiga market, and but that would translate to 40 euro going only to compliance testing, and we haven't bought a single component yet. So 40 euro of the product price, plus tax of course, would be just for compliance testing. That is out of the question. So as a result, the mains connected part must be an off-the-shelf part, and that's a brick power supply. I'm gonna try to show you that. Just a second. Here's such a brick power supply. Focus, focus. Hello. This is 12 volts at just over 4 amps, so it's a 50 watt unit. Here's the mains input. It's it's totally isolated and has passed all the safety tests. So this is just perfect for our application. And then of course a power supply may malfunction at some point. And a power supply has the power to destroy a lot of equipment. And then, of course, we would be liable for that. We need an insurance. Such an insurance is called product liability insurance, and of course, individual computers has that. And the way we approach power supplies is already approved by our product liability insurance. So let's jump right into the basic operation of a DC-DC converter, because our power brick only provides the 12 volt. And but we mainly want to make sure that the 5 volt are good. So we need to generate 5 volts from 12 volts, and that is done using a DC-DC converter. Let's take a brief look at how such a typical thing works. Here in the middle, that big block, that's the main chip. It takes an input voltage. In this typical application, it is 19 volts. In our application, it's 12. The output voltage in this case is set very low. Of course, these chips are mainly made for point of load regulation on PC main boards, and but they can of course be configured to output higher voltages, and that is the part that I've circled in red here. This is the feedback circuit. It's a very, very simple circuit, a voltage divider. The relation of these two resistors is equal to the relation of the voltage drop. So the feedback voltage that goes back into the chip makes sure that the voltage at this point, or here at the output, it's the same, is at a constant voltage, which we want to be 5.0 volts. And this is the exact point where we are cutting open our loop. And as you can see, there is nothing that looks at the current. This is only voltage, and this would be the circuit that causes a linear drop with load. Now the next one is current measurement. We need to build a little circuit that goes in between our load. So we need a little sense resistor. These sense resistors are they are very low, like 10 or 20 milliohms, and an operational amplifier with the proper feedback circuit. And then we have an output voltage that is proportional to the current that is flowing into our Amiga. And this current, or this voltage is something we can feed back into this resistor network, because resistor networks are ideal for adding and subtracting voltages. And this cable drop compensation, this compensation circuit, is something that I've built as my first prototype. And here's the performance of that first prototype. And of course, you can quickly see the problems that I had. It nicely holds up the 5 volts. The 5 volts even rise with the load, but overload behavior of this prototype was really bad. Yeah, that's not anything that you would want to send out to customers for several reasons. Actually, I've taken this prototype to CE pre-compliance testing, and it failed badly, so that was a bad thing. Then I had a hotspot. This is a picture from the FLIR, from the infrared camera, and as you can see, there are 2 hotspots. One of them is the sense resistor, and the other one, the one in the center that says 131 degrees, that is the DC-DC converter chip, and 131 degrees is way out of spec. So this is nothing that could be sold to anybody, unless you're in the boomerang business, because that thing is absolutely sure to come back after just a few days of operation. So that was a bad one. Second prototype would have to be more powerful. I have to think of better heat dissipation, higher efficiency, and this is the performance of the second prototype. In comparison to the first one, the voltage is a few millivolts, a few 10 millivolts actually higher, but still below that 5%, that 1% threshold that's required by the original specification. I have achieved this by using a more powerful DC-DC converter chip, and I have used an aluminum core PCB. Aluminum for Americans, aluminium for Europeans. This one also passes CE testing because I've done some other tweaks. Then, of course, there is a second compensation circuit in this one that measures the current on the 12-volt rail and feeds that back into the resistor network that forms the feedback voltage to the DC-DC converter. And then, well, this is really good enough. This thing went into production this way. Production is actually running. But I can't tell when this is going to be released because, well, Corona is delaying things worldwide, but we're not done yet. And there's a little problem with the LED. I've put a little LED in that DC-DC converter. Oh, by the way, you surely want to see a picture of the of that prototype. Let me attempt to show that. Just a second. Here is the PCB, and maybe you can see that it is metal in the middle, and I've added a few caps on this one for measurement purposes, and here is the huge inductor. This is where the cable is connected. Here is the 5-pin square DIN connector, and now back to our little problem, the LED. The LED is connected at a point where the voltage drop didn't happen yet. And that means the brightness of the LED changes with the load. And that can be quite irritating. So you insert a floppy and that LED gets brighter. That's really not a good idea. The eye is very sensitive to things that are happening outside outside your main focus in that peripheral vision, and you're always inclined to look that way if something changes, and the brightness change of an LED can be such an incentive for the eye to move. So we need a little compensation circuit, and that is regulation, constant current regulation. I have taken this picture from a website I found through Google. This is ledmeek.com. Very simple one. Please read the description there. I can see we're already crossed the 14-minute mark here. So let's look at the final comparison. I've put the diagrams here together with all the measurements. This is voltage, this is ripple voltage of that prototype is really lowest in that measurement series, except for the Amiga 600 power supply, which performs slightly better, but we're well under the original Commodore spec of 50 millivolts. And now what's left to say is thank you mainly to the, first of all, to the revision team. You've done a remarkable job doing this online revision on such short notice. OBS Studio, it's a great tool, very powerful and easy to learn, even for me, even for the hardware guy who really doesn't like learning new software things. And but this was kind of easy. LibreOffice is something I use every day, and I've used extensively for this development. Very nice thing. I encourage everyone to donate. Many thanks to the Amiga community. You might know that I've gone through some harder times in 2019. I just wanted to shut the company down, and yeah, I've had a lot of support out of the Amiga community and a lot of support from the team at Individual Computers. Um, we're all on a first name basis, meaning we can really say, well, that decision is crap, and that wouldn't be insulting to each other. My employees have done a good job uh, getting me personally out of that low state of motivation. I'm all motivated now, and I hope that you can see this on these new developments. Thank you for your time. Have lots of fun with the rest of revision, and yeah, see you at some real event in the future if Corona is finally beaten. Have a good one. Stay safe.